Good evening. I would like to thank the organizers for inviting me. I am very happy and honored that I can be on such a great conference, and that I can, with all the participants, honor the memory of Professor Julian Ławrynowicz. These results, which will be discussed today, are one of three parts of my master dissertation. First, we introduce some needed to prove the main theorem lemmas. So these facts are known but important for the proof. First lemma, let D be an open set and phi be a continuous function, then the function psi given by the integral is continuous. Next lemma, let D be a subset of Rn, G be the subset of Rn, and be the open sets such that D is a convex set, and such that the interval 0, 1 times D is the subset of G. Let phi be a CK class function, C infinity class function respectively, then the function psi given by the integral is also a C infinity, is also a CK class function, C infinity class function respectively. In addition, the following equation given by integral holds. Next lemma, let D be a subset of Rn, be a convex environment of the point 0 in Rn, F be a CK class function, K is greater or equal to 2, or C infinity class function respectively, and f of 0 is equal 0, and the gradient, which we denote here nabla of f of 0 is equal 0. Let G and Hij for ij from 1 to n be functions given by integrals by such equations. Then Gi are Ck minus 1 class function, Hij are Ck minus 1 class functions, C infinity class functions respectively. And f of x is equal the sum from 1 to n xij hij of x for x that belongs to D. Also, half of D square f over dxi dxj of 0 is equal hij of 0. In particular, the matrix hij of 0 is symmetric. Now let m be greater or equal than n and f of x be equal the sum from 1 to n xi xj hij of x in an environment of the point 0 where hij are ck class functions, C infinity class functions respectively, in an environment of the point 0. And the matrix Hij is symmetric. Determinant of the matrix Hij of 0 is not equal 0. Then, for any r from 1 to n, there is a linear exchange of variables Lr from Rn to Rn such that in an environment of the point 0, f of Lr of x, xn plus 1 to xm is equal to the sum from 1 to n xi xj underline hij of x, where underline hij are ck class functions, C infinity class functions respectively, and overline hij is equal overline hji for ij from 1 to n, and overline hrr of 0 is not equal 0, and the determinant of this matrix is not equal 0. Next lemma: if in an environment of the point 0 from Rn, n is greater or equal than to 1, f of x is equal the sum from r plus 1 to n ij xj squared plus the sum from 1 to r xi xj hij of x, where ej is equal plus minus y, j is equal from r plus 1 to n, the determinant of the matrix hij of 0 is not equal 0, and the matrix hij is symmetric. hrr of 0 is not equal 0. hij are C infinity class functions. Then there are functions large hij for ij from 1 to r minus 1 of C infinity class in an environment of the point 0, such that f of x is equal sum from r plus 1 to n ej xj squared plus 1 over hrr of x, the sum from 1 to r hjr of x xj squared plus sum from 1 to r minus 1 large hij of x xi xj, where x is x1 to xn. The determinant of the matrix of large hij of 0 is not equal 0, and the matrix large hij is symmetric. Using above lemmas, we get the following Morse theorem. Let f be a smooth function in a certain environment of the point A from Rn, n is greater than 1, such that f of A is equal 0, nabla f of A is equal 0, and the Hessian of f in the point 8 is not equal 0. Then there are a diffeomorphism phi of C infinity class and the integer number L, such that f decomposed with phi of x is equal minus sum from 1 to L of xi minus ai square plus the sum from L plus 1 to n xi minus ai square in a certain environment of A. The proof of the Morse lemma, we do using previous lemmas, and we bringing the case, this proof we bringing to the case x 0, a, in this case a equals 0, then we introduce the function f, we introduce the function f as the following sum using this lemma, where the functions hij are ck minus are in this case, in the case of the proof of the Morse lemma, are C infinity class functions, and the determinant of the matrix hij is not equal 0. Then we use a similar method to the proof of the Sylvester and Jacob theorem about inertia of quadratic forms. Here in this proof is also important the previous lemma about the differentiation function given by integral. Notice also that the Morse lemma is valid for n equals 1. Let f be a C infinity class function in an environment of the point A, such that f of A is equal 0, f prime of A is equal 0, and f b of A is not equal 0. Then there is a diffeomorphism phi of C infinity class such that f decomposed with phi of x is equal ix squared in a certain environment of A, where E is plus minus 1. Now we define the non-degenerate peculiar point. Let f be a C infinity class function in an environment of the point A. Then the point A is called the non-degenerate peculiar point of f when nabla f of A is equal 0 and the Hessian of f in A is not equal 0. The corollary of the Morse lemma is the set of the non-degenerate peculiar points of C infinity class function specified in an open set in Rn is isolated. Now we introduce some lemmas needed to prove the Morse lemma for the holomorphic function. Let m be greater or equal to n, f of z equal the sum from 1 to n, zl, zj, h, lj of z in an environment of the point 0 in Cm, where h, l, j are holomorphic functions, h, l, j is equal hjl for lj from 1 to n. The determinant of h, l, j of 0 is not equal 0. Then for any r from 1 to n, there is a linear exchange of variables Lr from Cn to Cn, such that in an environment of 0, f of Lr of z, zn plus 1 to zm is equal the sum from 1 to n, zl, zj over line hlj of z, where over line hlj are holomorphic functions, over line hlj is equal over line hjl for lj from 1 to n, over line hrr of 0 is not equal 0, and the determinant of over line hlj of 0 is not equal 0. if in an environment of the point of 0 in Cn, n is greater or equal than 1, f of z is equal the following sum plus the following sum, where h, l, j are holomorphic functions. Determinant of h, l, Lj of 0 is not equal 0. The matrix HLJ is symmetric, and HRR of 0 is not equal 0. Then there are holomorphic in an environment of 0 functions, large HRJ for Lj from 1 to R-1, such that the following equation holds, where determinant of h, large H, Lj of 0 is not equal 0, and large H, Lj is equal large H, Ljl for Lj from 1 to R-1. And finally, we have the Morse lemma for holomorphic function. Let f be a holomorphic function in a certain environment of the point z0 from Cn, n is greater or equal to 1, such that f of z0 is 0, nabla f of z0 is 0, and the Hessian of f in z0 is not equal 0. Then there is a biholomorphism phi in a certain environment of the point z0, such that f composed with phi of z is equal the sum from 1 to n zk minus z0k squared in a certain environment of z0. And the literature. Thank you for attention.
Thanks a lot for the lecture. Okay, so if someone has some question, please remark or comment. Okay, my question is the following. You can see that the statements of these two results are quite parallel. I would like to know if the tools that you use to prove the real version of Morse lemma are the same tools that you use to prove the.
Could you repeat, because I was looking here for participants, so could you repeat your question?
Okay,
please?
so my question is the following. Okay, the statement of these two results are quite parallel. Okay, very similar, and I would like to know if the tools that are used to prove the real version of Morse lemma are more or less the same tools that you need to use to prove the complex variables version.
These versions of these proofs are quite similar. We can see this looking at needed lemmas, but in the complex version, the proof has differences. For example, we have to use the branch of logarithm in the proof.
Okay, so thank you.